A lot about calculus actually winds up being defined, if you will, in terms of limits. So that's why we need to talk a little bit about limits, maybe more than a little bit, but we are going to talk the next few times here about what we call limits. And what we're going to do is start off with a nice little function here, and the function is f of x equals x minus 2 over x squared minus 4. And if I were to ask you, what value does this have at x equals 2? What would you get? Well, if I plug in x to be 2 there, I get what? I get 2 minus 2, that's 0. 2 minus 2 over 2 squared minus 4, let's just go ahead and write it out, 0 over 0. And what's wrong with that picture? 0 divided by 0. If you punch that in your calculator, or if you try to calculate that, what do you get? A non-answer, right? You can't do that. You can't divide by 0. Okay, so the function value at x equals 2, the function value is not defined. However, what we're going to look at is not really hinging upon that function being defined. Actually, what we can do is look at the values. So here's what we're going to do. We're going to look at values as x approaches 2 without actually getting to 2 in a table. We're just going to set this up in a table. All right, so what are some values that we could use for x approaching 2? We could use like 1.9. 1.9, we're talking about values that are close to 2 without actually being 2, because can I evaluate if x is 1.9? I think so. The value here I would get would be what? 1.9 minus 2 divided by 1.9 squared minus 4. Yeah, that's an actual number value. I don't have the 0 denominator, so I'm all good. All right, 1.9 minus 2, that'd be a negative 0.1, wouldn't it? Divided by 1.9, yeah, turn it on. 1.9 squared minus 4, okay, it's negative 0.39. So divide those two, 0.256. Okay, all right, well, that's good. But can we get closer to 2 than 1.9? How about 1.99? 1.99 would get us even closer to 2, and we'll make a point while we're doing that. All right, so that would give me what? 1.99 minus 2 divided by 1.99 squared minus 4. Doing all these by hand for just a second. I'll show you another way in just a second. But anyway, negative, that'd be negative 0.01 divided by 1.99 squared minus 4. Okay, it's negative 0.0399, and divide those out. .2506. See, kind of a, I mean, there's more after that, but okay. And let's do, so what would be even closer? We did 1.9, 1.99, so how would it get even closer to 2? 1.99, yeah, you kind of see. And we could keep going with that. All right, let's see what we get here. 1.999 minus 2 divided by 1.999 squared minus 4. Okay. So that'd be negative 0.001 divided by, get out of there, negative 0.003999. Okay. Divide those. Yeah, it gets kind of fun here. 0.2506 again. Do that right? Oh. Yeah, 0.25006. There we go. Put all those in. All right. Okay, so we kind of see a little bit of what's going on. Now, however, in this process, actually we need to look at the other side of 2 as well. You know, we looked at 2 coming into 2, x approaching 2, but this is from the low side of 2. We also need to look at what happens on the high side, if you will, of 2, above 2. So to come in from that side of 2, we'd have to get a number a little bit bigger than 2, but close to 2. How about 2.1? 2.1 would be a one that would be closer. And then we're going to do the very same thing with this that we did with get closer and closer. All right, so 2.1, it would be 2.1 minus 2 divided by 2.1 squared minus 4. So it would be 0.1 divided by whatever that is. 0.41. So 0.1 divided by 0.41, 0.243, 9. Blah, blah, blah. All right, then. Now, the thing is, what about on the other side of my x? Yeah, to get closer than 2.1, it's a little different than that side where we just add a 9 on the end. Here we're going to add a 0 in the middle. 2.01, that would be closer, wouldn't it, into 2? All right, so see what you get there. 2.01 minus 2 is 0.01 divided by 2.01 squared minus 4. Okay, it's 0.401. 0.249. 24937. And then better yet, 2.001 would be the next in line. With me on that? Getting closer and closer, trying to approach x approach 2. All right, so that would give me 2.001 minus 2. That's easy, 0.001. 2.001 squared minus 4 is 0.004001. So divide that. Like I said, I'll show you, if you haven't already, figure out a little nicer way of doing that. All right, 0.24993. Okay, here's the story then. We don't have a function defined at x equals 2. However, in this process, we can clearly see what's happening as x approaches 2. Can't we? As x approaches 2, don't these values seem to be approaching, getting closer and closer to 0.25 or a fourth? These are going to 0.25. 0.25. So the function values seem to be getting closer and closer to 0.25 as I go through this process. Now, what happens on this side? Basically the same thing. It's actually, these are going kind of downwards, but these are going upwards, or vice versa, I guess, if we really thought about it. But yeah, these also are function values are going to 0.25. That's the idea of limit. We would say that the limit as x approaches 2 of my f of x function, x minus 2 over x squared minus 4. The limit as x approaches 2 of that function is this 0.25 based on our observations here of using this table. Make sense? That's the idea of limit. It's a value, if we're talking about the limit of a function, it's a value that the function values approach as you get closer and closer to whatever number is that you're evaluating the limit at. That's limit. Okay? Now, we'll talk more about this function actually quite a ways down the road, but in a moment I'll also talk about something else. But I wanted to show you here, this is another nice thing. Not only is the calculator good for, graphing calculator is good for graphing, but they're also good for doing tables like this. If you have your graphing calculator, you might want to take it out. What you can do to get this, to generate this table, I won't make you do this by hand. You can use your calculators here to do this. What you do, just plug this into your on your y equals screen. The thing to note there, when you enter it into on most calculators anyway, the way you input it is important. You know, on the TI-84s we got y1, y2. So if I go in and put in y1, if I just put it in like this, okay, we're out of room here. Okay, all right, I think I almost got it there. If I put that in like this, y1 equals x minus 2 divided by x squared minus 4. Do you see something wrong with that? If I just input it just like that, what's wrong with that picture? What the calculator does is divide first, the way I entered it. So it's going to divide 2 divided by x squared. Then it's going to go x minus. So what do you got to do? You got to utilize parentheses. Yeah. When you input that on the on most calculators anyway, be sure to use parentheses around your top and your bottom. So x minus 2 divided by x squared minus 4. And if you have a question about the calculator, just let me know. I'll try to help. All right, but what I'm going to go to is go to the table screen. And on the TI-84s, you know, it's right above the graph. So I hit the second button and then the graph button to access the table. And actually, what we might have to do before that, if you haven't done this before, is if it comes by default set up where it picks the x values. If you want to set it up like we want to set it up, because their x values will be 1, 2, 3, 4. If we want to get special ones, here's a way you can get that. If you go to the table set, which is above the, on the TI-84s, is above the window button, second window, and set it up, and on the independent variable, which is the x value, tell it you want to ask. You want it to ask you what they are instead of auto. If it's set up on auto, and mine was for some reason, I don't know why I did that, but all right. So set it over to ask, and then go back to the table, and your table will be blank. Now we can do 1.9 and check our value. 1.9, 1.99. Let the calculator do the work for us. Okay. 0.25. Yeah, we did it right so far. 0.99. Yeah, we're all good. 2.1. 2439. Yeah, 2.01. And yeah, 2.001. And yeah, it's much quicker at calculating things than we are, so once we get it set up. All right, so yeah, if you have any question on getting that set up, just let me know. And there's other ways to do it too. But okay. All right. So let's try here. Well, let me mention this. So here's let me give you the formal kind of definition of limit too. The definition of limit goes like this. The lim. Oh, and then this also gives me. Well, let me do this over here. All right. Before I do that, though, let me show you this. There's also a notation involved here, and here's the notation. Talking about this. So back on that other problem, we had the limit as x approaches 2 of f of x, x minus 2 over a. That's very wordy. And so there is a compact notation here that we can utilize. We're doing the limit, so limit is lim, for good reason, right? X approaches 2, we're going to write that underneath the lim for limit, and we're going to do it with an arrow. That seems like a good way to do that, right? X approaches 2, X arrow 2. Okay? And then, here, we can either put f of x, if we've got it defined, you can actually specify x minus 2, and let's go ahead and do that here. We could just put f of x, but let's be real specific about it. Just put your function in there, the expression, and then equals 0.25. Much more compact way of writing that. But that's what it means. Okay. All right. So here's the definition of limit in general. The limit as x approaches a will be our letter designation, if you will, of a number we're approaching or something we're approaching. A will be that generalized letter that we use for that. So x approaches 2 or 3, whatever we want it to approach. The limit as x approaches a of the function f of x equals the limit L if we can make f of x as close to L as we like by taking x values to be sufficiently close to a, but not equal to a. Kind of wordy. That's where sometimes definitions go. By taking x values sufficiently, I mean that close to a, but not equal to. Isn't that what we did with that table? We were taking the x values closer and closer to a, and we were seeing that we could make f of x be as close to that L, the 0.25, as we wanted. We were very close with the ones we had. We were within 1,000 at least in several of those cases, and we could have gotten even closer, right, if we'd chosen x to be sufficiently small. And so that's kind of a formal definition. Okay, so you've seen that. All right, now, here's another thing. That last part, obviously not equal to a. Obviously equal to a in our first case there, we couldn't have done equal to a, but let's make a note here. Limits, in a lot of cases, don't really doesn't really matter what happens at a in our particular function, for sure. Note it doesn't matter what value or what happens at a, at your value, at x equals 2 or 3 or whatever it is, for a limit. It doesn't really matter what happens at the value, especially when you're talking, when you have an undefined scenario like we've had here. But to make that case even stronger, let's also look at this. Let's take another look at another function. Let's say f of x is a piecewise defined function. And the pieces are defined this way. First piece is just like we had, x minus 2 over x squared minus 4. And that's for any x that's not 2. However, if x equals 2, we're going to define it to be 1. With me on that? See what I'm saying? This one's not defined at 2, so I'm saying let x be, the function be this anytime x is not 2. 1, 3, 1.5, 1.9, whatever it is. Anytime x is not 2, this is your function value. But when x equals 2, the function value is 1. Okay? Well, what is the function value at 1? At 2. Well, we just said the function value at 2 is 1. But what is the limit as x approaches 2 of my f of x? Is it 1? No. No, it's not. Because as x approaches 2, we're talking about this one, aren't we? Because as x approaches 2, we're in this range. X is not 2. As we approach 2, x is not equal to 2, right? So as x approaches 2, we're in this range. Well, we already know what happens as x approaches 2 by the table that we did. So what's this limit? It's still 0.25, isn't it? Okay. So, yeah, just emphasizing here, the actual function value may match your limit, but it doesn't have to. The limit is what you're doing as you approach 2. It's not what happens at 2. Sometimes it is, and I'll get to that in a moment. But technically speaking, the limit is as you approach 2. It doesn't really matter what happens at 2, you see, because on the other one, it didn't matter what happened because it was undefined there, but it still had a limit, you see. So that just, again, emphasizing the fact that sometimes your function value may not even match your limit. And we'll speak to that a lot more later. But anyway.